Oh, this is another session on how to use Excel, and this is actually one of my favorites because it's talking to a very specific issue applicable to a machine shop. It creates a tool that you can take with you and use later. It also shows you a way of figuring out solutions to a problem that's pretty low tech, but quite handy and very effective using some graphing. So let's jump into this. So what we're after is to know how fast we can rotate the spindle on a lathe. So imagine a horizontal lathe might be something you had as a kid toy. It might have been a balsa wood lathe, or up to the high-end professional where we're working on metal and cutting it down to specific requirements, like an axle. You're trying to cut down an axle to create a smaller diameter to heat fit a wheel onto the axle, as you would with a railroad, putting the wheels on axles for cars or engines and such. So what you're after is, what speed do you rotate the engine? What speed do you rotate the motor on the lathe to rotate the spindle? And what you're after is two things. You don't want to go too fast that it overheats to the point and makes it dull and ruins the tool, or dulls it so it's not so good. So you don't want to go too fast, but you don't want to go so slow that it's wasting all your time and you're using expensive cooling agent fluid on there and having to recycle that. Perhaps you might be creating an environmental, having to deal with filtering and recycling of that. So you're looking for the optimal speed range. May not be a very precise number, but you're looking for at least a feasible range, a reasonable range. So we're going to jump into that with some Excel tool. So as I've talked to, we want to control the speed of the spindle. We're going to take the pressure of the point to be a different issue that can be based on manufacturer requirements. But we're looking at, for this, the spindle speed not too high or not too slow. So what we're after is a sequence of processes. We're going to take the example. This is a cutoff tool. So imagine the picture in the top left. If the furthest up part is in a chuck and the other part's out, and there's a cutting tool there, darker element coming in from the left. You can see that it's being pushed into the material. The stock, in this case, based on the arrows, is rotating counterclockwise, which creates a downward cut at the cutting tool. This could be an edge, or it could be a very narrow edge almost to a point, such as a cutoff tool might be, or all that, if you're cutting it all the way down, cut it off, or you're just taking it down to a certain diameter. So we're going to start with, in this scenario, a 3-inch diameter round stock. And we want to determine the cutting speed, and the standard for that, that's most common, at least fairly common, is to measure that in surface feet per minute. So if you imagine the bar stock as it goes by the tool sees a tangent right there, and it's, whether it is real tight radius or large isn't too important. On the tool point, it's down at the very small fraction of an inch, not quite molecular, but it's somewhere in that kind of range. So you can think of that as a surface speed going by, almost as if it was tangential, and there's a pretty straightforward equation to figure that out. We'll get into that. And we're going to go with an assumption, and you can change this in the what we're going to set up based on manufacturer recommendations. But we're going to use an 1,800 surface feet per minute is what I called the upper control limit for the maximum surface feet per minute that you want the stock to go by and the tool to be cutting into. Any faster than that, would probably be overheating it or just overwhelming it, or maybe setting up a vibration and a chatter. Neither one would be optimal for this scenario. So you may ask, so why don't you just set it and let it go? Well, if you keep it constant from the very first speed, such that it was under that surface feet per minute, as the diameter gets smaller and smaller, the radius gets smaller, and the effective surface feet per minute decreases significantly. And as it goes along, the surface feet per minute is slower, and you're reaching the point where you're bordering on wasting time and fluid, and you can crank up the RPM on the spindle and still maintain the surface feet per minute under 1,800 surface feet per minute, the control limit. So we're going to use some equations to calculate these speeds at varying RPMs and at varying dimensions as we're doing the cut down, and compare that to our 1,800 limit. So the cutting speed at any particular instant is equal to the spindle speed, we're going to use revolutions per minute, times a special constant that we all know is pi, as in 3.1415. We use the symbol, Greek symbol pi there. You're familiar with it. It's used in the circumference of the circle, 2 pi r, the area, pi r squared. Same pi. Uses the inch diameter of the stock divided by 12 inches per foot. That's because our surface feet per minute is a feet, and our diameter of the stock is in inches, so we need to convert, so we're using the same units. So our equation for figuring out the surface feet per minute, the length of material that is going by the point, is the revolutions per minute of the spindle times pi times the diameter at that instant, then divided by the 12 to get it into feet so that we have the same units. Again, in this equation on the slide, you can see the asterisk is above the number 8, or the time sign mean the same thing. And we're going to be using the built-in constant value for pi in Excel, so we don't need to typing in lots of decimals. It can handle pi to a pretty good resolution and level of preciseness. So we're going to launch Excel on the computer using the formula in the prior slide, and we are going to build a table of speeds at given RPMs and current instantaneous diameter of the tool, and we will plot that along from a time perspective. So as the diameter decreases, we'll be able to see how the surface feet per minute decrease, and we will plot that for varying RPMs of the spindle, see how all those compare to the target maximum 1,800 surface feet per minute upper limit. So it's going to be little intensive, lots of equations, but once we get them in there right, we'll be able to replicate them. But we have to be really careful about absolute versus relative addresses. But that's what we're here for. So let's press on. So each cell, as I said, is going to compute the surface feet per minute given the radius, diameter, and the RPMs of the spindle. And we're going to chart that 1,800 to use that as a visual upper line. We can, at this point that I created this slide, I was perceiving we can put that at a secondary y-axis, but actually it can be on the the primary axis, so we don't need to add that unless you want to put that on just so it stands out a little differently. Okay, so we're gonna create the chart. It's gonna create a two-dimensional array of various steps on the sizes of the spindle and then the speeds. And this is part of the assignment that's just verbalizing here. So create the array. From that, we can create a graph where each RPM has a separate color. We make a legend that is so represents that. Then I want you to take a look at it and ask yourself, so what does this tell me? What can I take away from this? What can I infer from this? And as the instructor in me, in addition to that, I'd like you to think, well, where else could I use this methodology? So this is kind of neat. We could use it. This is the real world. But what I just went through actually has a lot of places in life where I can come up the values of different things like that and plot them. Maybe it's for figuring out when to which loan for a car or a house based on different things. You can plot this, so it's a good tool in that sense. So here's a resulting table. This is what it would look like in our example when it's finished built. Behind each one of these cells in the middle is a formula, an equation, and that is going to look at what's the current dimensions. So we're going along the left y-axis. We have what's the current diameter. Well, it start at 8, and we can work down to 0.25 or stop or in between if you're just creating a step down in the bar stock, like you were creating an axle inset for a railroad wheel going onto an axle. So it's going to look at the diameter, but it's also going to be using the RPMs. And we vary these, and once we build the equation here, we can replicate it once we're careful with our addressing relative versus fixed. So we're going to create all those combinations plotted by the RPM vertically, and then also plot the maximum upper control limit 1800. It's handy to replicate this here so that it'll chart across as a line. Makes it much more visibly easy to see. This would be the sample chart that we could be building. You vary the colors, tweak the title as you so desire. You can got some flexibility, but this would be one example. Wherein, let's take the top one. So this blue one, that's where it's 400 RPM, and at 3-inch diameter with the motor going at 400 RPM, the surface feet per minute going by the tool point is up here in the 3,000, 3,500 range, which is almost twice the max recommended speed for the cutting tool. It would deform it, overheat it. Probably not a good choice. So if you follow on along to the red line, you see, oh, the first RPM that's underneath that is this gray one, which is 2,000 RPM. So that, to me, that would say if you wanted to start with the highest possible speed on the spindle, but still keep it under the surface feet per minute, your 2,000 RPM would be the choice. And you could stay with that. As you get along here at the 1-inch range, you're going to be going down closer to 500 surface feet per minute. So it's going to be going a little slower as far as max cutting. So you could probably look up here and look at the blue line, 4,000 RPM. So you could double the spindle speed, double the surface feet per minute. And at that diameter, you are still under the max 1,800. So you can see where you can start here, and depending upon how quickly and easy it is to change speeds on the fly. If it's just an automatic, you just press a button and change it. It'd make some sense to transitioning up to these higher speeds as you get down to that diameter. If you have to stop the machine and reset stuff, then your setup time is going to eat up any efficiency and time that you would gain by going to the higher speed. So there's a human judgment call there based on the setup you have to work with. Okay, so let's jump over to the spreadsheet. So the PowerPoint was early on in the activities section, I believe, lessons, and then further along is the problem itself, which is reflected by this. So what you will see is bring up the spreadsheet. Of course, it's going to say, click here to edit so you can do things with it. And I highly recommend, as soon as you bring it up, click that and go to File, Save As, and give it a new name. The intro will make a recommendation as to how to structure the file name. We'll give it some other name so that you're not clobbering over the initial problem. Put your name in it, date, that sort of thing. So the words on the left is a condensed version of the PowerPoint slides. So you will recognize that as pretty much one and the same. So let's go over here to the meat and potatoes of this. We crank it up a little bit. Let's see how much we can get it. Well, that seems to be where we can go. So, as you recall, so this is our equation. Let me see if I can put a couple tabs in there just so I can get it on the same screen. No, can't. So we've got RPM times pi times diameter divided by 12. So what we want to do is put a formula that equates to this in each cell. Wherein for that cell, it reflects the RPM for that column and that diameter for that row. So let's jump in. So I'm going to put my cursor in cell K7 right up here. And formulas, the current designations, you started with an equal sign. If you've learned other systems, you can also learn a plus sign at work too, but Excel goes for equal sign is where they try to motivate people to. So let's go for K6. So we're going to start with, I'm going to do, I'll right click, left click still here. I'm going to now click on the RPM. So that brings up the RPM, and then we're going to multiply. I'm going to press the multiplication to asterisk right above the 8 key, multiplied by, so we're going to now use the pi function. I'm going to just type in pi paren. We could have looked it up above, or I can do that in a moment, but since I know, I just wanted to go ahead and type that in because it's a little faster that way. So we got pi times the radius, which is right here, J7, and then divided by, so it's the symbol right below the question mark. This class, you certainly know that. And divided by 12, the constant to convert it back. So so the answer, it'll come back at 78.5. Now, while we're cursing here, you can look up here and you can double check. So the equation we put in was K6 times pi times the diameter, J7 divided by 12. Okay, well, we want to have that basic equation in all of these cells, but we don't want to have to type it in each one individually. That would be a little nightmare. That's why we learn the tricks and the ins and outs, because it will save us time. So let's think first about just going vertically down this column so that we're keeping 100 RPM, but the diameter is going down. So in our equation, so the RPM is going to stay the same. So that RPM was K6. So in our equation here, we've got K6. Well, we're going to want to move this down, and you're probably ahead of me. You're going to say, oh, he's going to use the copy square root. Yes, I will, but if I do that right now, it's going to end up with some weird numbers, and trust me, those won't be right. So I'm going to not do that yet. So I'm going to look at this. So the K6, as I bring that down, I want it to stay on row 6. So what am I going to do to this equation such that I can replicate it, but it's going to stay on row 6? Right, I'm going to put a $sign in there. So I put a $sign in, so then I can hit enter. Now, when I copy this and pull it down, it's going to, so when I'm down here, it still says 6. Now, let's look at the J. Well, it so happens that these, I didn't move sideways, so the J was good at keeping that as a J. So that should work for that row. But now let's think about, so I copied those on down and just do a double check. It's always good to check. So it's K6 times pi times the radius J18 divided by 12. Perfect. So now let's, what do you think? Can we replicate these sideways and just highlight all that and then grab this and pull this over there? Well, we could try that, but we're going to end up with a bunch of errors, aren't we? So let's go back and look at this. So we've got the 6 is locked in because this row is always going to be where the speeds are. But as we pull over here, that K is going to turn to an L, isn't it? So what was a K6 here is now going to turn to an L6. Well, actually, that's okay, because at this column, the speed we want is 500, which is L6. So perfect, that worked out nicely. So now if I'm going to pull this down, what's going to happen? It's going to stay, it's now looking to multiply a diameter, thinking the diameter is K9. Right, so the L worked fine, but the diameter didn't. So we don't want to do that because it will be not right. So when we copied this over and went to the side, this was a relative address and it changed. We want it to stay in the J column. So now we go into this column, and in front of the J, we put a $sign and press enter. So now when we copy this equation over, it's going to stay in the J column and get the diameter. So now when we copy it over, that looks a whole lot better. So we kept the 6 constant here, and we kept the J row constant there. So now we can pull those down, and that looks really good. Do a quick visual check. We're down here. It's the L6 and the J17. Perfect. So now we've got those. We can highlight all that, copy that over, and voila. Let's do a visual check here. We got a P6, perfect, times pi, times the diameter J18, perfect, divided by 12. All right, worked. And let's go over here and populate this column. Since I just highlighted one cell, it kept it as 1800. If I had happened to have 2 of those, it may have progressed it or incremented it. So that worked out. That copy is sometimes, you got to be careful because it may increment on you. If it thinks it's a sequence, it's like that was January, and you did that to the cell and had January, it's going to probably turn into February. So there's, see, so sometimes maybe too smart for you, and it may do something you didn't expect. In that case, it worked perfectly. Okay, let's take a pause here a second. So we've got all that. Now we want to create the chart. I like to highlight all the data, go to insert. I like to start with recommended charts to see what it comes up with, and lo and behold, a line chart is exactly what I wanted. So we'll click that, say okay, tell it to put it down here. Okay, it's got to be enough on the screen. The incremental. There we go. Now it's stuck. Okay, so now we need to change some elements here. For instance, you highlight the chart title. You could put in cutting speeds and surface feet per minute. I have for decreasing. Okay. Well, you can see you can spend a lot of time. So I will help you create more of that. For instance, I would say cutting speeds and surface feet per minute for decreasing stock diameter for various spindle RPMs. Then you want to add in your titles, your axis titles. This is a newer element to Excel in the last few years. It's kind of handy. Click on that, and you highlight the things that you wanted to add in. So then it'll put it in for you. You highlight it, and you type it in from there. So this grabbed a little bit earlier than I expected, so it looks a little unusual there. So I'm going to click in the middle of the data set here, do a select data. So the data it started plotting didn't need to be the word inches. So get rid of that. Okay, there we go. So it went too far, and what it didn't need to plot that as a column. It was plotting the RPMs. So these are the RPMs. You can highlight that, select the data, series 1 name. Highlighted that right there and told it that. And voila. So just replicate that. Depending upon what you highlight to begin with, you can do those all at once by telling it the row, or you can incrementally do them singly and clean it up. So now you're looking at this, as we saw on the PowerPoint slide. We jump back to that. So here's what we had in the PowerPoint slide real fast, what it looks like. Now down here somewhere, insert a text box. Insert. Here we go. It's over here, this version. A text box, and type in your observations about the data, how you interpret it into actual application, et cetera, et cetera. Here, what I like to do, you see how the got the text box here. See how you get the grid behind it? That's kind of unprofessional. So I like to highlight or click on that box, do a right click, bring up format shape, go to fill, tell it solid fill, give it a white, might as well leave it at 0 transparency, and voila, it looks a lot better. I like to highlight it, do some, click on review, click on spelling, and it'll tell you where some misspellings are. You don't see where that scenario is, but obviously it was off. But I will say change it, wherever it is, ignore it. Change that. Also, how you can use the spell checker and go ahead and save it as per the instructions. Anyway, I hope that was useful. As I'm trying to get to, what you can see is charting stuff out like this and putting it on the line. What you just created is a very graphical, visual way to interpret a feasible solution set, as they might call in a math class. In reality, to you, it's to me, it's the workable, reasonable ranges that'll work there, and then you apply some human interpretation of what you're what are you trying to do as far as saving time or changing speeds. Does that have an impact, make implications like that? Well, hope you enjoyed it, and future occasions come up where you can apply this technique and see how to do that. And in the meantime, save it as a tool. So if you've got a machine, set it, go back to the RPMs, to what you have available in the machine, and reset the upper control limit for what your manufacturer or your experience tells you to do. Anyway, hope you enjoyed, and thank you much for your attention. Have a great day.